Unit 2 SYBSC. In Unit 2, there is a topic, first topic, transistor biasing. The basic function of transistor is to do the amplification. A weak signal is given to the base of the transistor and amplified output is obtained in the collector circuit. One more important requirement during the amplification is that only the magnitude of signal should increase. There should not be change in the signal shape. This increase in magnitude of signal without any change in shape is actually known as faithful amplification. In order to achieve this, means are provided to ensure the input circuit, that is base to emitter junction of the transistor, remains forward biased, and output circuit, that is collector to base junction, always remains reverse bias during the all part of the signal. This is known as a transistor biasing. In this chapter, we are going to discuss topics: faithful amplification, why need transistor biasing, inherent variation of transistor's parameter, stabilization, essential of transistor biasing circuit, stability factor. Faithful amplification. The process of raising the strength of weak signal without any change in its general shape is known as faithful amplification. The theory of transistor revealed that it will function properly if its input circuit, that is base to emitter junction, remains forward biased and output circuit, that is collector to base junctions, remains reverse biased at all time. This is then the key factor of achieving the faithful amplification. To ensure this, the following basic condition must be satisfied. That is, proper zero signal collector current, minimum proper base emitter voltage at any instant, and minimum proper collector emitter voltage at any instant. Proper zero signal collector current. What do you mean by this? Consider a NPN transistor as shown in the figure. This is the NPN transistor. Now, during the positive cycle of the signal, base is positive with respect to the emitter. That means there will be a positive voltage at the base with respect to the emitter. This hence make the base emitter junction forward bias. This will cause the base current and larger collector current to flow in the circuit. The result is that the positive cycle is amplified in the collector circuit, as you can see from the figure. During the negative half cycle of the signal, base emitter junction get reverse biased. That means here we will have a negative rather than positive. And positive at the emitter. Hence, no current will flow in the circuit as the base emitter junctions is reverse biased. The result is that there is no output due to the negative cycle of the signal. As you can see here, there is no uh, cycle over here. The result is that there is no output due to the negative half cycle of the signal. Thus, we get amplified output signal with its negative half cycle completely cut off, which is unfaithful amplification. Now introduce the battery in the circuit, BBB. Magnitude of this voltage should be kept such that it keeps the input circuit forward bias even the during peak of the negative half cycle. When no signal is applied, a DC current will flow in the collector circuit due to the VBB. As you can see, if no circuit is applied, a small current will be flow through the collector of the transistor, that is load resistant RC, that is IC, due to the DC supply of VBB. This is known as a zero signal collector current, capital IC. During the positive cycle of the signal, the input circuit is more positive and more forward biased, hence the collector current increase. During the negative cycle of the signal, the input signal is less forward biased, but still there will be a positive at the base with respect to the emitter, and the collector current decreases. In this way, negative half cycle of the signal is also appear in the output. Hence, the faithful amplification result, as you can see from here, we get negative cycle at the output too. The result of the value of zero signal collector current should be at least equal to the maximum collector current due to the signal alone. That is, zero signal collector current should be greater than or at least equal to the maximum collector current due to the signal alone. Proper minimum base emitter voltage at any instant. In order to achieve the faithful amplification, the base emitter voltage VBE should not be falls below the 0.5 volt for the germanium or 0.7 volt for the silicon. The base current is very small until the input voltage overcrosses the potential barrier at the base emitter junction. The value of this potential barrier is 0.5 for germanium, as you can see, and 0.7 for the silicon. Once the potential barrier is overcome, the base current, hence the collector current, increases sharply as the base current is the actual source for the collector current. Therefore, if the base emitter voltage falls below this value, that is less than 0.5 or less than 0.7, 0.5 and 0.7, we will get unfaithful amplification during this part, and this result unfaithful amplification. Minimum proper collector emitter voltage at any instant. Now, for faithful amplification, the collector emitter voltage VCE should not be less than 0.5, as you can see, or 1 volt for the silicon, 0.5 for the germanium, and 1 volt for the silicon. This is called knee voltage. When VCE is too low, that is less than 0. In this region, or 1 volt, less than 1 volt, that is in this region for the silicon transistor, the collector base junction is not properly reverse biased. Therefore, collector cannot attract the charge carrier emitted by the emitter. and hence a greater portion of them goes to the base. This decreases the collector current while base current increase. Hence the value of beta falls. Therefore, VCE allows to fall below the knee voltage during any part of the signal. That part will be less amplified due to the reduced beta factor, and this will result into the unfaithful amplification. However, when VCE is greater than knee voltage, the collector base junction is properly reverse biased, the value of beta remain constant, resulting in a faithful amplification. Transistor biasing. The proper flow of the zero signal collector current and maintenance of the proper collector emitter voltage during the passage of the signal is known as actually the transistor biasing. The basic purpose of transistor biasing is to keep the base emitter junction properly forward biased and collector base junction properly reverse biased during the application of the signal. This can be achieved by adding the base battery as we have seen with the transistor. The circuit which provides the transistor biasing is known as biasing circuit. Now, example. An NPN transistor has VCC 6 volt and RC 2.5 kilo. Find the maximum collector current that can be allowed during the application of signal for the faithful amplification and minimum zero signal collector current required. First point. For the faithful amplification, VCE, that is collector to emitter voltage, should not be less than 1. Therefore, we have to make sure that it should not go less than 1. That means 6 volt VCC minus 1 volt, that is we have to design only for 5 volt. Now, collector current which passes through the RC is VCC divided by RC, that is 5 volt divided by RC, that is equal to 2 milliamp. During the peak of the signal, that is positive peak, the minimum zero signal collector current required is half above and half below. 2 milliamp, that is 1 milliamp above and 1 milliamp below is 1 milliamp. And during the negative peak of the signal, if you can see 0 to 1, 1 to 1, that is 2 milliamp. If 2 minus 1 minus 1, that is 0. And during the positive cycle of, you can say 1 plus 1, 2 milliamp. Inherent variation of the transistor parameter. Now, current amplification factor beta is actually the ratio of change in collector current to the change in the base current, known as current amplification factor beta. Now, in practice, transistor parameter such as beta and base to emitter voltage are not same for every transistor. Even the same type transistor has been used. To give an example, BC147 is a silicon NPN transistor with a beta varying from 100 to 600. That is, beta for one transistor may be 100 and for the other it may be 600. Although both of them are BC147. This large variation in parameter is a characteristic of the transistor. A major reason for this variation is that the transistor is a new device and the manufacturing techniques have not much advanced at that time. And for this instance, it has not been possible to control the base width. It may vary. For some, it is widened and for some, it is narrowed. Such a small variation result in large change in the parameter such as beta. The inherent variation of transistor parameter may change the operating point. resulting in unfaithful amplification. It is therefore very important that the base biasing transistor network should be designed such that it should be able to work with all transistors of one type, whatever may be the value of beta or base to emitter voltage. In order to say the operating point should not be depend on the transistor parameters. Stabilization essential of transistor biasing circuit stability factor. In this three topic, we will see first stabilization. Stabilization, the process of making operating point independent of temperature change or variation in transistor parameter, is called as a stabilization. Once the stabilization is done, the zero signal current, that is collector current IC, and collector to emitter voltage VCE, become independent of the temperature variation or replacement of the transistor. The operating point is fixed now. A good biasing circuit always ensures that stabilization of the operating point. Need of the stabilization. Stabilization of operating points is necessary due to the following reason: temperature of independency of IC, individual variation, and thermal runaway. Temperature independence of collector current IC. Now, collector current in a common emitters configuration is IC equal to beta times of IB plus ICEO. This ICEO is actually related to ICBO. This is a leakage current in a base collector emitter junction and in a collector base junction, and these are equal to beta times of 1. The collector leakage current ICBO is greatly influenced by the temperature change. A rise of 10 degrees centigrade double the collector leakage current, which may be as high as a 0.2 milliamp for a low power germanium transistor. As a biasing condition in such a transistor are generally so set that the zero signal current, that is IC, is equal to 1 milliamp. Therefore, the change in IC is due to the temperature variation cannot be tolerated, and this achieved by only zero point 0.2 milliamp base current. It is necessary to stabilize the operating point or to hold the IC at the constant value in spite of the temperature variation. Individual variation. The value of beta and VBE are not exactly same for any two transistors, even of the same type. Further, VBE itself decreases when the temperature increases. When a transistor is replaced by another one of the same type, this variation changes the operating point. This is necessary to establish the operating point, that is, to hold the current IC, collector current, a constant value irrespective of individual variation in a transistor parameter. Third, thermal runaway. The collector current of VCE, the collector current of IC, as we have seen above, is beta times of IB plus beta plus 1 leakage current into the reverse bias junction of collector to base, that is ICBO. The collector leakage current, this ICBO, is strongly depend upon the temperature. The flow of the collector current produces the heat within the transistor. This raises the transistor temperature. And if no stabilization is done, the leakage current, that is ICBO, also increase, and that result into the self-destruction. The self-destruction of unstabilized transistor is known as a thermal runaway. In order to avoid the thermal runaway and consequent destruction of the transistor, it is very essential that operating point is stabilized, and that is IC has to be kept constant. In practice, this is done by causing the IB to decrease automatically with the temperature increase by the circuit modification. Essential of the transistor biasing. As we have seen or studies that for the transistor biasing we needed, why we needed for faithful amplification. For faithful amplification we have to ensure the three things: proper zero signal collector current, proper base to emitter voltage, proper collector to emitter voltage. Plus we have seen that to have a stabilized circuit we need to make sure that current IC remains a constant value in spite of the thermal runaway, temperature change, or inherent variation of the transistor. The biasing circuit should be designed by keeping these all points in the mind. The biasing network should meet the following requirement essentially. It should be ensured that the proper zero signal collector current, and it should ensure that VCE should does not fall below 0.5 volt for germanium or 1 volt for the silicon at any instant. And it should ensure the stabilization of operating point. Stability factor. What is a stability factor? The rate of change of collector current with respect to the leakage current at a constant beta factor in IB is called stability factor. That means how much the collector current change with the leakage of the collector current voltage, collector current in a reverse bias at some constant beta and IB. Now, S equal to change, that is different derivative of collector current with the derivative of the leakage current at a constant B and IB. Now, collector current in VCE in a common emitter junction configuration is IC is equal to beta times of IB plus VCEO, collector emitter leakage current, which is actually nothing but 1 beta plus 1 collector base leakage current. If we differentiate this equation with respect to IC, we will get 1 equal to beta times of IB divided by beta times DIB divided by DIC plus beta plus 1 DIC divided by DICO. To find this, actually this is nothing but 1 upon S. We will can write easily beta plus 1 by 1 S. And rearranging the equation, we will get stability factors as equal to beta plus 1 divided by 1 minus of beta IB DIB divided by DIC. Thank you.